Today is a special certain day, so we're going to be looking at hearts. Yep, that's right, a maths channel doing a Valentine's Day special before GTA 6. Anyway, this is a heart. In everyday life, you might consider it to be a pretty simple shape, but when we try to graph it with a function, it's actually rather difficult. Firstly, unlike the majority of functions you know and love, get it, a heart has neither infinite range nor domain. In fact, it's not even technically a function because it doesn't map every input to a single output. But luckily there are already closed shapes like this which we can graph, namely the circle and ellipse. But the thing with these two shapes is that they're defined implicitly. They're of the form f of x, y is k, instead of the more standard y is a function of x. And this means that they can be harder to A, visualize, and B, figure out what you need to change to get your desired result. Here, imagine y equals x minus 2 all squared in your head. You're probably thinking of something like this, and if I up that exponent to a 3, you know that the shape will change, but the root will be the same. Now consider x squared y cubed equals 3xy squared plus 2. Yeah, you have no idea what that looks like, do you? Here it is. And if I tell you that I'm going to change the 2 to a 1, the graph doesn't shift down by 1 like you'd expect. Instead, it does this. And the final complication comes from the fact that a heart is a pretty weird shape. It has these strong curves here at the top, but then it's basically straight at the bottom. And even worse, it has these two sharp points. But without further ado, let's get into it. Starting off with the creation of Gabriel Tobin, who was trying to visualize surfaces with singularities and other sharp points with the help of computer software, when he found this 3D heart equation. Now this one is just really impressive. Like, I could try and explain how to solve this, but I think it's better to just admire how perfect this is. Okay, admiration time is done. Let's move on to the next one, which has a much simpler formula of r equals 1 minus sine theta, which forms this nice heart here. If you're unfamiliar with this notation, these are polar coordinates, where the distance of a point away from the origin depends on the angle it makes going anti-clockwise from the positive x-axis. And I think this is pretty clear to see here. When theta is 0, sine theta is 0, and so our point is 1 away from the origin. When theta is 90, sine theta is 1, and that's why we get this point that's on the origin. And this shape here is called a cardioid, presumably stemming from the word cardiac because, well, it looks like a heart. And cardioids are a specific example of limacons, which are of the form r equals a plus or minus b sine or cosine theta. If the absolute value of a is the absolute value of b, then you get a cardioid. Otherwise, you just get some weird whatever shape. Alright, next up we have probably the most complicated looking one, which is this. Again, if you're not familiar with this way of constructing an equation, this is what's known as a parametric equation, because the values of x and y are dependent on a parameter t. I can't get it to show every point at once, but if you watch the point of intersection, you can see that it traces out the shape of a heart. Using parametric equations is really useful when modelling. For example, let's say that you throw a ball straight forward at 10 meters per second, and ignoring any air resistance, you want the equation for the ball's path through space. This is kind of hard to do from just the information we have, but what you could work out fairly easily is how the ball's horizontal and vertical displacements change with time. In this case, we can use good old s equals ut plus half at squared to work out that our horizontal displacement x is equal to 10t, and the vertical displacement y is minus 4.905 t squared. And then we let t vary and we can see the path being traced out. And in this case, we can get an explicit equation for this via a little rearrangement. Now, this is a nice case where we can get the explicit formula, but that's not always the case. In the case of our heart, for example, we could write t in terms of x, and eventually get that t is the inverse sine of the cube root of x over 16, and then sub that into our equation for y, but due to the restricted domain of the inverse of sine, we only get the top part of the heart. Well, that's unfortunate, so let's look at our next one. This one looks familiar, and it should do because it's just the first equation, but we swapped around y and z and then set z to 0. And geometrically, what this looks like is taking the cross-section of the 3D heart right in the middle where it's at its biggest, or alternatively projecting the 3D shape onto a 2D surface. Now this bit's kind of short, but if you want a challenge and you know about implicit differentiation, try and figure out the coordinates of the two peaks of the heart. Anyway, if you're trying to impress someone, this one's the one to go with because it's simple whilst actually looking like a heart. Now so far, all of these are ones that I found online, but this last one is one I came up with myself, and one for you to try out as well. We're going to start with a sine curve, and then throw in a coefficient on that x to squish all of it in a bit. And then here's the real magic. We multiply this expression by the square root of 4 minus x squared. And what this does is it restricts the domain of the function to the interval 2 to minus 2. So we get this thing here, which is a kind of vaguely coloured in circle. So now we just need something to give us that heart shape, and that comes in the form of subtracting 4 minus the absolute value of x from both sides. Then you can just divide by something to make it less elongated and add a constant to center it roughly at the origin. And there you go, your own custom heart graph. And that's all for today. Make sure to comment your favourite heart, and thanks for watching.